So, good afternoon, and thank you for attending this brief talk. This is Sahar, and I will present the work titled On the Sensitivity of Residual Networks for Time Series Classification by me and Dr. Mu'taz Ahmed. In the next minutes, we will introduce the main idea here, back it up with a bit of background, then see what has been done in the literature. We will then get to the experiment and show what we have got from there. Let's start by time series classification being the context of this work. Time series composed while data captured over time, then represented as sequences of numerical data points. Modeling these sequences has materialized many applications, and deep learning models have delivered a notable performance there. Residual networks, ResNets, shine as a leading performing model for time series classification. These models' performance relies heavily on the architectural design decisions taken and the settings of their hyperparameters values. Here, we focus on analyzing the direct influence of these decisions and these values on the model's performance, specifically the ResNets. So, we will proceed toward a deeper understanding of the impact of different architectural designs on the model performance, besides its reaction to the hyperparameter changes and their interactions. Let's first talk about ResNets. They compose basically of convolutional layers, each followed in this design by a batch normalization layer and activated by a ReL function. Each three layers form a block, and multiple blocks form the model architecture. The model ends with a global average pooling and a softmax activation, and that results in a probability distribution over the classes assigned to the input record. Note the blocks here are connected by linear shortcuts. Those are distinguishing ResNets from other models and known as residual connections. Getting back to the literature, we can see different deep learning models have been involved in such studies as ours, like CNNs, LSTM, and attention-gated CNNs. Frequently, we found the number of layers and the learning and dropout rates studied. Into time series lags, the length of an input record at time series have gained researchers' attention. Some models have been investigated further, such as RNNs, and the importance of the model's hyperparameters have been always emphasized. For ResNets in particular, multiple studies have tried to get the best of the model utilizing different methods, either to optimize the architecture or to provide enhanced input records. Moving to the experiment, 4 factors have been analyzed. Those are the depth of the architecture, defined here by the number of the blocks, and the width of the model, that is, the filter size at convolution layers. Both dropout and learning rates have been also applied in different values. A fractional factorial design of 2 to the power of k has been applied to trace the impact of these factors' variance. Two types of data considered, those are univariate and multivariate time series, almost 140 datasets. At the table shown, we can see the detailed values of the model hyperparameters, including the selected factors. Each factor has been set to relatively high and low values in order to examine the impact of their variance on the model performance, and that conform also to the design selected for this experiment. Considering this combination of 4 factors, each with 2 values, we had 16 different variants to experiment with. The table shows the assigned values for the considered factors in each variant, and note the change vertically in the factors' values and horizontally within variants. Let's recall the essential architecture that we presented earlier. It forms the first variant ResNet 1 architecture with 3 blocks started by 32 as the filter size at the first block layers, then filters of a double size at the later blocks of layers. This is a representation of the largest variant has been experimented, ResNet 16, with 9 blocks and a starting filter size of 128. The same practice of enlarging the filter size as the network gets deeper followed here, and that is an inherited practice actually in the literature whenever ResNets implemented. Note that there is a dropout layer implemented here after every convolutional layer, and this design decision in particular will be mentioned once more later. There were more than 2,000 experiments running these 16 variants, each on the full set of datasets. The experiment's results built the input to an ANOVA test that reported a significant difference in the variance performance. Next, related pairs of variants compared to understand the model reaction to the change within a single factor. The results show that the depth of the model has no significant impact on its performance unless the network gets extremely deep. The width of the model also does not impact the classification results. On the other side, larger values of learning rate facilitate a higher performance, while variants of zero dropout rate outperform other variants of higher dropout rates. So its higher rates of learning, lower rates of dropout, and simpler networks are much better than more complicated ones, especially those are much deeper. What about the interplay between the considered factors and the characteristics of the time series data being classified? Which factors should be considered based on those characteristics? Dropout rate should be always considered, and it's almost the same for learning rate unless the data has many classes or lengthy records. For the number of blocks and filter size, it varies, while the same rules just mentioned seconds ago applies here too. But what if these findings are influenced by our design decisions? What about less dropout layers or more epochs? How this would affect the overall results? So we conducted more experiments. We ran selected variants for more epochs, and we tested architectures with less dropout rates. What we mean here by less dropout rates is that we implemented the dropout layers after each block instead of being applied after each convolutional layer. The performance of variant ResNet 16 has been enhanced when trained for longer time and has less frequency of dropout. However, it could barely meet its comparative variance performance from the original experiment, that is ResNet 15, which was trained for much less time. The same applies to other variants, for here as another example. Note the performance of the new version of ResNet 2. It represents a possible competitor for ResNet 1, the best performing variant from the original experiment. Still, it could not outperform ResNet 1 once it gets trained for the same number of epochs. Based on these extended experiments, the results from the original experiment sustain. In the future, similar work could be initiated to trace different sets of hyperparameters, other intermediate values, rather than the ones investigated here, or even analyze different design decisions while building the studied architectures. Regarding the datasets involved here, they were of one type, that is, a single class per series, and data of multi-classes can be the subject of a similar experiment for sure. Let's conclude this talk and bring back its main points. Simpler models surpass, learning rate comes first, and be careful with dropouts. Thanks for listening and being here.